Hello, I'm Kay Strang. You can check me out on my website, quantumid.science, where you can find more detailed analysis and material on my series of 6 podcasts, Hunting the Identity of the Quantum. The previous podcast dealt with the criticism contained in the EPR paper and how the thought experiment described in it, involving position and momentum, was never properly addressed, but manipulated to form a secondary thought experiment involving spin directions and magic particles that communicate over large distances faster than the speed of light. This was supposedly proved to be correct by experiments that used light waves. In this podcast, I would like to highlight how Schrödinger's wave equation and criticism of the notion of the superposition of particles was distorted and used to support the pursuit of the fantasy of a quantum computer. There were many critics of the Copenhagen interpretation, and Schrödinger was principal among them. His famous cat was his attempt to demonstrate how ridiculous the interpretation was, but it somehow backfired and has been used ever since as a demonstration of quantum weirdness. The existing wave equation in classical wave mechanics is linear, and in mathematics it means that solutions can be added together to give a further solution, and this is considered a superposition of states. It is not a peculiar feature of quantum mechanics as such. It was appropriated from the physics of vibration and applied to discrete particles. It is ridiculous to move from this to concluding it must be a feature of macro objects such as cats. Schrödinger observed in his 1935 paper on the present status of quantum mechanics that one can easily show, for example, by including a cat in the system, quote, the quite ridiculous case with the wave function of the entire system having in it the living and the dead cat, pardon the expression, mixed or smeared out in equal parts, close quote. So Schrödinger found it difficult to regard the Copenhagen interpretation as representing reality. His conclusion in the same paper is that, quote, the reigning doctrine rescues itself, or us, by having recourse to epistemology. We are told that no distinction is to be made between the state of a natural object and what I know about it, or perhaps better, what I can know about it if I go to some trouble. Actually, so they say, there is intrinsically only awareness, observation, and measurement. Close quote. The Copenhagen interpretation of Schrödinger's equation is that it describes a free particle of mass m moving in one dimension. Squaring the result of the equation changes the imaginary number I, which is the square root of -1, in the equation to a real number, and uses a factor to normalize the solution to arrive at 1, which is the probability of 100%, and that gives the location of the particle. In this interpretation, the superposition of states is interpreted as the electron being in many different positions at once. Squaring the wave function removes the imaginary number I and provides the probability of finding the particle at a given location. When the electron is located and the measurement taken, the wave function collapses, and what I suppose can be imagined as a cloud of probability and uncertainty coalesces around a single actuality. In order to preserve the discreteness of particles, this extremely convoluted procedure is elevated to the status of ontological truth. It is important to deconstruct the wave equation and examine what each part of it means. I have done this in the essay on my website. For now, it is important to note that the equation is made up of partial differential equations representing sine and cosine waves. It also includes the imaginary number, square root of -1, or I, which has possibly helped reinforce the belief that everything is observer dependent. The word imaginary is a misnomer, as a number is a mathematical device discovered in the 17th century to avoid lots of tedious trigonometry. When I is combined with a real number, the combination is referred to as a complex number. There is a useful technical note in the book on Oliver Heaviside by Paul Nahin, which I've included in the additional material section of my website. From his explanation and from the brief description of the wave equation, I hope it becomes clear that the wave equation is describing a real physical process. And it should be noted that while waves can be superimposed on each other, causing all sorts of interesting patterns, particles cannot. Nevertheless, the Copenhagen interpretation promoted the idea that a particle can be in many different positions at once, and this formed the basis of the search for a quantum computer. This search began decades ago and is now a multi-billion-dollar industry with nothing very much to show for itself. Supercomputers based on classical technology, which obviously use electrons but in a classical framework of electronics, outperform them. It was AlphaFold, a standard AI system developed by Google's DeepMind research institution, that solved the structure of proteins. To get an idea of the scale, there are around 10,000 proteins in the human body alone. Contrast this with recent claims by Google on the supremacy of their quantum computer, which were discredited by their arch-rival IBM. The history of the subject shows that while there are numerous theories on the development of a quantum computer, no fully functional practical example exists. The online magazine Quantum Zeitgeist gives an account of the history of quantum computing. Quote, "The concept of the quantum Turing machine, QTM, was first introduced by David Deutsch in his 1985 paper, Quantum Theory, the Church-Turing Principle and the Universal Quantum Computer. In this work, he proposed a theoretical model for a quantum computer that could simulate any physical system, including itself. The QTM is based on the idea of a Turing machine, which is a mathematical model for computation developed by Alan Turing in the 1930s. One of the key features of the QTM is its ability to exist in a state of superposition, meaning that it can process multiple possibilities simultaneously. This property allows the QTM to solve specific problems much faster than a classical computer. For example, Deutsch showed that a QTM could factor large numbers exponentially faster than any known classical algorithm. The QTM has been influential in the development of quantum computing and has inspired many subsequent models for quantum computation. However, it is still essentially a theoretical construct, and significant technical challenges must be overcome before a practical implementation can be achieved." End of quote. The article was written in February 2025. I do not find this at all surprising, as the concept of a quantum computer is based on a false premise, namely that the electron, as a discrete particle, can be in many different places at once. Another online magazine, Live Science, in 2024, in its article on the history of quantum computing states, quote, "One of the biggest barriers for today's quantum computers is that the underlying hardware is highly error-prone. Due to the quirks of quantum mechanics, fixing those errors is tricky, and it has long been known that it will take many physical qubits to create so-called logical qubits that are immune from errors and able to carry out operations reliably." End of quote. In attempting to fit continuous wave phenomena, which can be in a superposition of states, into the binary and digital framework of a computer, one could easily end up with the flaws identified in the current examples. It strikes me that the best example of a quantum computer is the human brain, which can process actions, emotions, and thoughts at the same time. Neuroscientists talk of different types of brain waves at different frequencies. And if this is combined with the wave theory of light and matter, a unifying picture of nature emerges, which I believe is more compelling and coherent than a menagerie of particles. So my conclusion is that the quantum is a useful bit of mathematics that somehow escaped, a bit like a virus or meme, and infected our understanding of what is real. If you want to find out more, please visit my website at quantumid.science, where you will find more in-depth downloadable essays, book lists, and original papers by some 19th and 20th century physicists. This is the final podcast in my 6-part series. I may do a further series later in the year on pursuing some of the ideas and intuitions of 19th century physicists, which I believe cast a great deal of light on, amongst other things, current cosmology. Thank you so much for listening.